Neurips 2024 part 4. This paper is about an online visual agent that's based on a graphic user interface that acts with a device, like in this case, it's an Android device. So imagine you have an agent that acts on your smartphone and executes tasks. For example, find me the next restaurant that has good tacos, book me a flight to Barcelona, find me the best price, etc. So those kinds of tasks. And what's interesting here is that this is a reinforcement learning problem. It comes out of the Levine lab at Berkeley et al. And I think it also tangentially touches upon the concept of reasoning. And let me explain why. So the problem is you have an agent that interacts with a virtual world, so with a website, for example. We're using a smartphone just as the device that actually is acting here. And you could use a PC, you could use a Mac, you could use things like that. So there are certain actions that can be taken. For example, you can click on stuff, you can type stuff, you can press home button. So the kinds of stuff that a smartphone allows you to do. Basically, when you navigate the world on your smartphone, imagine an agent doing that for you. And the goal here is to find a reinforcement learning algorithm that can do that better. And particularly the authors emphasize the fact that they want to do two things. They want to be able to keep learning on the go, so learn from the stochasticity of the actual event and keep improving while they're learning. Now, they're not mentioning sort of the Richard Sutton plasticity of learning type problem, which is, I think this is still a model that eventually freezes its weights. But of course, you could extend this to the next level and say, well, why don't we just have continuous learning? But that's not where they're going. But what they are trying to do is basically find a way to algorithmatize reasoning. So when the agent is on a path that is maybe not so good to find the best flights to Barcelona, maybe the agent is, because of complications on the websites that it's particularly on, it makes a mistake and then derails into nonsense. That's the kind of problem that needs to be solved. And the way the authors solve this problem is by having a self-evaluation function. So this reminds me of the large language monkeys situation with the Stanford professor, Mortasani, I believe is her name. So what we have here is a large language model as an evaluator that evaluates each step in the training process. So I guess this is really a couple of things in one, right? We have agentic training, so agents, big deal. If you look at Ilya Sutskever's keynote that he gave at Neurips, he spoke about the future, which is agents, reasoning, understanding. So this is all in line with that. This is a real implementation of what he was talking about. First, we have an agent. Now we have reasoning. So reasoning just means that I want to be able to navigate through the world with given the stochasticity of the models that I'm exposed to, and hopefully find mistakes that early on and then fix them. And therefore you have to define what the evaluator is even trying to evaluate. So the fundamental problem here is, if I tell you find me the best taco in Barcelona, then the agent could be doing a Google search for tacos in Barcelona, and then go on Yelp, and then maybe that's the wrong path. Maybe Yelp is not going to find you the best tacos. So you want to be able to early on decide, I'm not going to go on Yelp, I'm going to go on this website or that website, or I'm going to do a smarter search. Maybe I'm going to look for magazines that have been recently talking about food, or I'm going to look for celebrity quotes that mention tacos because maybe they know better what's really hot in the city. So those are the kinds of things that really, I believe, are achievable with enough data. Again, to go back to Ilya's talk, if we have enough data and then enough of a general pre-trained model, we could have that knowledge stored somewhere and then extract it by online reinforcement learning, which just means that we actually are changing the weights while we're learning. And we can do this in virtual space. This is not a robot that can kill people. So that's what's good about online reinforcement learning in virtual space. So I think that this paper really captures a couple of things, in my opinion. Again, first, the question is, okay, how can we pre-train this model in such a way so we have a certain understanding of what it means to search the web, to find stuff, and to have goal-oriented actions? What does that even mean, right? That's the pre-training phase. They use the offline reinforcement learning and something called advantage-weighted regression, which is kind of like a regression method that looks for, predicts the next action based on the past actions and gives the next action a reward if it gives you a better potential outcome than the one before. The actual reinforcement learning algorithm that they use, the online reinforcement algorithm, uses what's called cross entropy, and that's sort of a classification algorithm that looks at possible actions based on the knowledge that you have and the states that you're in, and the actual pre-trained knowledge of what kind of actions could be good or bad, and then assigns Q values to these online real-time actions, and thus hopefully finds better ways to solve the problem. And I think, again, if you think about this sort of in a more philosophical way, right, what we're doing here is really building a reasoning agent. So these agentic models are just preludes to reasoning, because an agent has to be able to reason, because an agent is a multi-epoch AI-driven machine that has to be able to reason. It has to be able to understand when do I make a mistake, and that's partly explained in the paper, that you have this problem of, well, how do I even know I'm wrong? How do I know I'm wrong? Like, how do I know when I made a mistake? Do I have to wait till the end of the epoch, or can I maybe do it a bit earlier? So what is a mistake? We use large language models evaluators for that, but I think this is, how do you correct an agent when it's on the wrong path? How do you even know what's a wrong path? What is the ground truth? Those are really important questions. In my opinion, the paper tangentially comes across. I mean, we're talking about a paper that's trying to implement a model, so they're using data sets, they're evaluating themselves against data sets and things like that. So this is not something you can use in the wild yet, but I still think it's really interesting to have these types of works presented, because they open up all these questions, right? How does an evaluator evaluate whether an agent's on the right path? If I want to find the best taco in Barcelona, how do I know that while doing a Google search going on Yelp is the wrong path? How do I evaluate that? Maybe that's a good evaluation method based on, but I think if I have enough pre-trained data, I can actually find out that, no, that's wrong, you should go do something else, because the Q value of searching in a fancy magazine with celebrities that particularly like tacos is maybe a better way to find the best hot taco restaurant in Barcelona than doing just a Yelp search. So those are the kinds of subtle things that a work like this, I think, can uncover. The authors are mentioning some of it, but I guess to summarize, I just want to focus really on two things here. One is the offline reinforcement learning paradigm for pre-training a model. So this is the equivalent of the GPT in text-based learning. Offline reinforcement learning is kind of like the GPT of action-based knowledge base. Build an action-based knowledge base of what actions lead to what results, and then fine-tune it with online reinforcement learning and large language model evaluators that actually reward the actions of the online reinforcement learning algorithm by giving it maybe partial rewards or full rewards. That's I think still an open question. I think that goes into the question of sparsity of rewards. when we have, let's say, an action where, okay, your goal is to give me a recommendation for a taco, and I will know only at the end whether this recommendation was better than that recommendation. That's relatively difficult to evaluate, because how do I even know what's a good taco versus a bad taco? So those are the kinds of subtle questions. But again, I think we're on the right path here. We have to define what the problems are, and part of the problem of online reinforcement learning is to understand what to evaluate and how to know that you're on the right path and the wrong path. This goes back to Move 37 in AlphaGo, where maybe certain strategies could look really weird. Like I just said, for example, if I want to get the best taco and the agent starts searching celebrity magazines, I might say, hey, what are you doing here? Like, I'm asking for tacos, not for celebrities. Well, let me do the search, because celebrities, the hip hop scene in Barcelona really likes tacos. So that's the kind of, Move 37 type potential that I see in this work. And like I said, there is also tangentially, we're talking about reasoning here, which is part of the idea of Move 37, which is, okay, what does it mean to reason? What does it mean to understand? And I think the path towards training a model to reason is going through the questions of what does it mean to be wrong, and how do we fix that? And then we can use reinforcement learning to actually do it. The reinforcement learning part is the methodology, but the questions of how to evaluate an agent and how to define when it's on the wrong path and how to give it rewards for right or wrong, those are the kinds of questions that I believe can be solved, and they can be solved with large data and very general models. And again, the analogy would be offline reinforcement learning for pre-training, and then online reinforcement learning for fine-tuning. Thank you.